This is video help for problem 28.2, and actually it's crucial for you because the written help that you've got is for an earlier version, and it was changed, and so you've got to actually pay attention and use this video help to get the full picture. We start off with an alias signal coming from, adding up different portions of the actual, spin density or magnetization over, the alias parts. This formula represents the math behind when you're overlapping your images and getting the pictures that you had gotten before when you first studied aliasing. What we've got is, a number of coils here. This little index N covers the, NC coils, and P covers all the different replicates, in your aliasing. So you get a fully aliased signal. You're going to take that alias signal and extract from it M hat over the whole range, that you want for it, the full where all the protons are. We represent this by this matrix, but that matrix is not square in general because in general we have more equations than unknowns. And what that means is that we've got to somehow balance the different equations to get the best solution we can that, in general can't exactly solve all of them, but we'll solve them all best. And that's what gave this, this pseudo-inverse, solution that you found in your discussions in the text. The idea then is this is not square, beta dagger, beta is square, you can invert it and you can get M hat, and we need to look at some examples now. We've chosen then for 3 coils and, an alias portion, 1 overlap, we've got a 2 by 3, or actually I would say 3 by 2, 3 rows by 2 columns, matrix that's not square. And so we'd have to look at its adjoint. Hermitian adjoint, by the way, is just take the transpose and complex conjugate. So you have this, the rows and columns get switched. And by the way, since we're thinking about just one component, the x component of the fields, then we can take this as real. That would be complex if we had the x and the y component. Now, we just chose this to, roughly speaking, simulate the coils that you can see in the figure in the chapter. The first coil AB and the last coil BA are kind of symmetric, and then the middle one kind of gets a signal. We're looking at 2 pixels. We're trying to find the magnetization at 2 places, Y1 and Y2. As a simple little toy for us. And for that, we've given you a signal, alpha, beta, gamma for all 3 coils that's aliased. Now, in part A then, as I said, we want to find out M hat. We want to disentangle all this aliasing and alias signals and extract the M hat. The actual unaliased reconstructed image is what we want. Now, you can just crank away. By the way, when you do it, you'll get intermediate numbers, like 1.1 and 0.61 and beta dagger beta. You know how to multiply then, a 2 by 3 times a 3 by 2 to get a 2 by 2. I just go these 3 times these 3, and then times these 3, and that gives me the top row and so forth. Your usual matrix multiplication. And by the way, you know how to get an inverse of a 2 by 2, the resulting 2 by 2. This is a 2 by 2. And I got some numbers here you can check against if you want. I got a 1.1 and a 0.61 here. I got a 0.8379 in the denominator here because it's the determinant. And I get a 1.16, 1.405 in the part, actually the S hat, the beta dagger S hat part. And you can do this without all of that help. you'll get an answer, you'll get a kick out of it because for the 2 pixels, you're going to get it that it looks like, just as if you were trying to look at our little step function. The neat thing is, in this particular case, if you try to do an alternative, and an alternative would be to just replace everywhere in this thing, replace beta dagger by any A dagger. Again, it's going to have to be, a 2x3, something or other. And then that beta dagger also by A dagger. That is, why? Here's what we started with. We got 3 equations for 2 unknowns. The least squares is the best solution. But if we multiply by any A dagger of this, so here we have that, now we get something that's a 2x2 again. A dagger B, B is a 2x2, and you can invert it. And so this was just kind of a handy-dandy way to get any other solution in general. And then you could solve it, you could put it in. And by the way, I have a simple little example that you can just as well use if you want, or do anything you like. I took A dagger to be just 1, 0, 1, minus 1, 0, 1. And the reason for that is that it kind of throws away one of the equations. You'll see in a second. You can do this, see what you get, and you know what? You're going to get exactly the same answer as before. Why? Here's why. I actually wrote out the 3 equations. This is what our matrix represented. I wrote them out. And I just solved the first 2. And when I solved them, I got exactly the same answer. Now I'm giving you the answer even. That I got in the original pseudo-inverse stuff. Aha. In fact, this is an exact solution for all 3 equations. I arranged it, the numbers, so that all 3 are solved. That isn't going to happen in general. And especially it's not going to happen when you have, some uncertainty, some errors in your measurements. Well, that's what we tried to do in part B. Redo this thing now with S hat this, which now the 3 equations are not completely compatible, and now you're looking for just the best answer, the most compatible answer, and that's what the pseudo-inverse does, and you'll get an answer that's a little different from the previous. And by the way, if you tried your A dagger alternative to see, you would get a little bit different there. This is the more realistic thing. So I hope that helps.